All right, hello and welcome to Mr. Linford's live stream for March 23rd. Today we're going to be discussing a couple topics students have emailed me about. First, we're going to review some topics from last Thursday about rationalizing the denominator of a radical expression. And then someone else also emailed me about going over section 10.2, which talks about rational exponents. That was the stuff we covered on Friday. So let's start in section 10.6. We're going to first review the first problem from the independent practice. Now, remember, the idea with working with radicals in terms of division, or when they're written as fractions, the idea is to simplify them, or to, I guess, perform this division. You want to write the expression in a way where the radical is not in the denominator. Okay, we do not want to have a radical in the denominator. So the thing that we have to do is we have to multiply the top and the bottom, because remember, that's the really only way we have of changing around the fractions. The only way we have of changing around fractions is to multiply the top and the bottom by the same quantity. So we're going to do that. We're going to multiply the numerator and the denominator by a value that gets rid of the fraction in the denominator. I don't care how complicated it makes the numerator, really. I just need to get the denominator to be a value that is not a radical. Okay? So this is a cube root of 6x squared. Okay, this is a cube root. I need to multiply it by things that make the radicand perfect cubes. So if I'm going to work with a cube root, I better multiply by a cube root so they can actually multiply together. All right, so I'm multiplying by a cube root. Now I have 1/6 in the first radicand. What could I do to make it a perfect cube? Well, I could multiply by 2 more 6s, right? To get a perfect cube, I would need 3 6s. So if I have 1, just multiply by another 2. And then here we have 2 x's. Well, if I want a perfect cube, I better just multiply by 1 more. So let's see what happens when I multiply the cube root of 6 squared x to the top and the bottom. Well, the top is going to be 2, and then the cube root of 6 squared and x squared. And then the bottom, we're going to have the cube root. I won't simplify anything just yet. I want to see how it all multiplies together. 6 times 6 squared is 6 cubed. X squared times x is x cubed. So when we simplify, the top becomes, well, let's see, that's 2, and, well, 6 squared is 36. Are there any cube roots in that? Let's see. 36. What are some cube roots? 8? No, that doesn't go into it. 36, let's see, another cube root would be 27. No, that doesn't go into it. So we're just going to leave it as is. 6 squared. And then x squared, well, that's not going to be a cube root because I only have 2 x's, not 3. And then the bottom, let's see. The cube root of 6 cubed is, well, that's just 6. And the cube root of x cubed is just x. So here is how we're going to go and simplify down this radical. We're taking the radical, and again, this is the same thing as this. They're the same expression. It's just one is the simplified version of the other, okay? And again, don't really care about how complicated that numerator becomes. Mostly what we're concerned about is getting the radical outside of the denominator, making sure that denominator does not contain a radical expression. All right, let's go ahead and try another problem. Again, if you have any questions or comments about the work we're doing, or if you want me to go over another problem, feel free to let me know in the live chat. Let me know which problem and from what section, and we'll definitely make sure to go over that. And especially if you have any questions about the work that I'm doing, if you're confused on any steps or want me to slow down, just let me know. All right. Messing with my mic here. All right, now we're going to go through a problem where instead of having just a radical expression in the denominator, here we have multiple expressions in the denominator. We have 2, in fact, and 2 of them They both have radical expressions. This should remind us, I think I said in the lesson for this section, I said this should kind of remind us of what we did when working with polynomials. We could kind of think of this almost like a binomial. It's not really, but in fact, it actually would be a monomial because these are all just numbers we could combine together. But we can think of it like a binomial, and we can kind of treat it that way. Here are two expressions, and they both have radicals in them. What is the way that we figured out to get rid of these radicals? Well, again, since this is a fraction, we have to multiply the top and the bottom by something, right? That's the only way we can change a fraction around and still have it be the same fraction. So how do we go about doing this? Well, in the lesson, we discovered the difference of squareds. That formula for multiplying binomials and for multiplying binomials together and getting a binomial was the method that we wanted, because what it did was it forced us to square the values, and any middle value that we would have was canceled out. Let's take a look at that. First up, we said to multiply by the difference of squareds, you have to multiply by the conjugate of the denominator. The conjugate was the exact replica of the denominator, the exact replica of the expression, except the sign was different. Here we have a negative instead of a positive, okay? So really the conjugate is the other factor when you're trying to do the difference of squareds. When you're trying to multiply the two things that are identical, except one sign's different than the other. So we're going to do that to the top, and we're going to do that to the bottom. Now, some people might be saying, hey, can't you simplify the square root of 12? You can. I'm thinking of just holding off and doing that at the end, just reminding myself, just because I feel like when I go through and do all this multiplication, I'm going to have to simplify anyway. So I figured might as well just, simplify at the end one time as opposed to having to do it a couple times. All right, so let's go and multiply these together. And when multiplying, because it's all distribution, we're going to use the box method for this just to make it a little more organized and helpful. All right, let's start with the top. I'm going to try to do that towards the bottom here. We have 3 root 3. That's a terrible 3. 3 root 3 and negative root 2. Make sure you include the signs. And then we're going to multiply that by 4 root 12. My stylus is messing up. 4 root 12 and negative 3 root 2. So when we go and perform this multiplication, we're going to do individually each component, sort of like we're distributing each thing through one at a time. So 3 root 3 times 4 root 12. Well, 3 and 4 make 12, and 3 and 12 makes 36. And then 3 root 3 and negative 3 root 2. Well, 3 and negative 3 makes negative 9. Root 3 and root 2 makes root 6. Now let's do negative root 2 times 4 root 12. Negative and 4 make negative 4. Root 2 and root 12 make root 24. And then negative root 2 times negative 3 root 2. Negative and negative makes positive 3. Root 2 and root 2 makes 2. So I guess for this one we can go and quickly simplify this to just say that it will be 6. Now that's our numerator. So let's go ahead and plug that in. Let's try to copy all this down. 12 root 36. And you know what? Let's just go ahead and start simplifying this. I mean, why not? Why write the square root of 36? That's just 6. So 12 times 6. I was going to try to save it until the very end, but oh well. 12 times 6 is 72. And then we have to subtract 9 root 6. That's not going to simplify. And then we have to subtract... okay, let's just go ahead and simplify all this together. I'm trying to be clever, but it's not working. All right, 4 and root 24, negative 4 and root 24. So we said this is just going to be, this first one is just going to be 72. And then root 24. Well, the square root of 24 can break down into the square root of 4 times the square root of 6. So that's 2 root 6. And if I multiply that by negative 4, I get negative 8. So really, this is negative 8 root 6. So we've gone through and we've simplified down our multiplication. Maybe I probably should have simplified the square root of 12 first, but whatever. We're able to do it later on. So, and as we notice, the like terms are diagonal from each other in the box method. So we can go ahead and combine these together. We have 72 and 6, so that should be a 78. And then we have negative 9 root 6 and negative 8 root 6. So that should be negative 17 root 6. That's what we get from multiplying just the numerator. Now let's go ahead and do the denominator. So let me clean up some space here. We'll set the problem up again, box method style. We have 4 root 12, and we have 3. Oh my gosh. We have 3 root 12. And then we have again a 4 root 12. And this time a negative 3. Oh, I'm sorry, it's root 2. I'm just messing up all kinds today. All right, root 2. All right, now as we go and multiply these through, we want to see what happens with the difference of squareds formula. We expect to square the outer values and the inner values, and these middle terms should cancel out. But let's see how that actually plays out. So 4 root 12 times 4 root 12. 4 and 4 makes 16. Root 12 and root 12 makes 12. So we really have 16 times 12, and that's going to be 192. So let's see, 192. And then let's do the ends here, the last term. That's going to be 3 times negative 3 is negative 9. Root 2 times root 2 is 2. So that should be negative 18. Negative 18. So we get whole numbers when we square them, obviously, right, because we're squaring square roots. Now let's take a look at what happens when we get the middle terms. Let's see. Let's try to fill in this spot right here. 4 times 3 is 12, and root 12 and root 2 makes root 24. And then for the last spot here, let's do 4 times negative 3 is negative 12, and 2 and 12 is, so that's root 24. We notice, or hopefully we notice, that again, the like terms are diagonal from each other, and these are going to cancel out because of the same thing, right? One's positive, one's negative. So the terms are going to cancel. I don't even need to worry about simplifying things down because we know that the same thing, just one's positive and one is negative. So here is how the difference of squareds formula is working. It's forcing us, we're not changing the initial fraction, or the initial expression, I should say. Rather, all that we're doing is we're very carefully picking a value to multiply to the top and bottom so that we're forcing it to have a whole number expression on the bottom, I guess is what I want to say. We're very carefully forcing it to not have radicals in the denominator. So again, we might make the numerator more complicated. That doesn't matter, right? Again, all that we care about is making the denominator not have any radicals in it. So let's go ahead and let's write that denominator out. It's 192 minus 18. So 192 minus 18 should be 174. And there we go. There is our simplified version of the original. Again, the reason it's simplified is because it doesn't have a radical in the denominator. Now, make sure you're comfortable using this idea of the conjugate. Multiplying by the conjugate is key here because it's allowing us to use this difference of squareds technique when going about simplifying. That's the whole trick to this, is you got to use the difference of squares to square each value to get rid of the radical and to force those middle terms to cancel out. Now let's switch up sections and let's go to section 10.2. In section 10.2, we learned about rational exponents. And I love this section because it's a really interesting way of thinking about radicals and really connecting radicals with exponents. Because in fact, radicals and exponents are kind of the same thing. When we work with square roots and cube roots and fourth roots, it's the same thing as working with exponents, like saying squaring things, cubing things, or taking the fourth power of things or whatever. It's just we have to think about it in a little different way. Okay? But really, radicals and exponents are pretty similar in the ways we work with them. Now, the first thing I want to do is remind ourselves what it means when we have these fraction exponents, how to read them. Okay? So the first thing that we should do is let's take a look at x to the 3/4 power. I'm going to split this up into x to the 3rd power times the 1/4 power. We could also have split it up into x to the 1/4 power times 3. This is just the power rule, if you remember. The power rule. And this said, you can express the exponent as a product of exponents by taking the expression and then taking that whole expression to another power. So the power rule said a to the n to the m power is a to the n times m. Okay? So let's go ahead and use this idea to actually try to understand or try to re-express this this expression with a rational exponent, a fraction exponent, into something with radicals, into something with roots. So in the first one, when we see the 4th root of something, or the 4th power of something, that means we're taking a root. Any fraction, anytime you have a fraction as an exponent, it means take a root. And the denominator is the index. So when I say take the 1/4 power of something, I'm saying that basically means take the 4th root of it. So I'm going to take the 4th root. And what am I taking the 4th root of? Well, x to the 3rd. There's my radicand. Now this is the same as if I were to take the 4th root of x. That's what this part signifies. Take the 4th root of x. And then if I took that whole thing to the 3rd power. Okay? These expressions right here are equivalent. We're saying take the cube root of something and then take the 4th root of it. That's the same as taking the 4th root of something first and then cubing it. And you can try this with numbers, right? Let's plug a number in. Let's plug in 16, okay? So, example here, and then I'll get back to the problem. Let's take 16. We could take 16 cubed, and the 4th root of that should be the same as the 4th root of 16 cubed. Again, that's a terrible 3. Let me fix that. Okay. So 16 cubed, 16 to the 3rd power, is 4,096. So we're going to take the 4th root of 4,096. So when I do that, I should end up with 8. All right. Let's see if that works for the other side. Now let's take the 4th root of 16. Hopefully you know that's just 2. And then we got to cube that. So 2 cubed is actually 8. So hey, it works. So these expressions are equivalent, which is really helpful because a lot of times students prefer one way of reading it or the other, which is fine. You can pick which method you like. But this is what it means when it comes to rational exponents, when you have a fraction as an exponent, and how you read that in terms of the radicals, things that we've been working with before. So let me clear some space here. And we're going to tackle this problem, and it should seem very similar to work we've done before with exponents. We're going to use all of our properties of exponents that we started with in the semester and we've seen in previous classes. But this time, what we're going to do is we're going to try to understand how this, I guess I want to say how this denominator is now affecting us. All right, it looks like, Amelia, you would like me to go over question 3 from the independent 10.2 practice. You got it. So let me finish up this one from the exit ticket. We are going to use our rules of exponents to simplify this. Now, hopefully, we can see that we can rearrange our multiplication into this expression, right? I just reordered all the terms by the associative property. 3 times 2 is 6. And then now we have x to the 3/4 times x to the 2/3. So x to the 3/4 times x to the 2/3. This is going to be a situation where we're going to have to add the exponents together. So remember, when you go and multiply like bases, you have to add the exponents. So we're going to have to add 3/4 and 2/3 together. So I'll write that down. And you can go and make common denominators. You can go and figure that out. I'm going to cheat. I'm going to use my calculator. I'm going to type in 3/4 plus 2/3. And I'm going to use the fraction command under math to get 17 over 12. Might as well just use technology to help simplify. All right, so we have this expression, right? And I think I asked you to write the answer in terms of radicals. So what we need to understand here is that this is the radical. The 6 has nothing to do with the radical. It's on the outside, okay? Remember that exponents only affect what they're immediately touching. So this part is the only thing that's going to have the radical affecting it, okay? So 6 is on the outside. Do not include 6 in the radicand. So in this problem, the numerator is the exponent, and again, like before, the denominator is the root. So let's take the 12th root of x to the 17th power. That's basically what this exponent is saying. Take x to the 17th and take the 12th root of it. Now, hopefully you're realizing, wait a minute, we can simplify things down here. In fact, we could rewrite this to be the 12th root of x to the 12th times x to the 5th, right? If you have 17 x's and you need a group of 12, well, I can get 12 of them in there. So I can make one group of 12, and then how many do I have left over? Well, 5, but that's okay. That doesn't fully simplify. So 6 and the 12th root of x to the 12, and the 12th root of x to the 5. So that's just 6. The 12th root of x to the 12th, these just cancel. That's just an x. And then we have the 12th root of x to the 5th. So here is how we've gone through. We've used our properties of exponents to combine things together. We then understood how rational exponents really mean radicals and exponents together. So we rewrote the expression. And then once it was rewritten, we saw, hey, here's a great way of going and simplifying it. Sometimes students ask me in this step, when they see x to the 17/12, they say, what if instead of writing it as a mixed number, or as a improper fraction, what if we wrote it as a mixed number? So 17/12 would be 1 and 5/12. So that would be 1x and x to the 5/12, which would just be x and the 12th root of x to the 5th power. It would be the same thing. So sometimes people prefer to think of it in terms of mixed numbers. Others prefer improper fractions. For me, I like the improper fraction method, but that's just me, okay? Again, if you have any comments or questions, let me know in the comment section. Let's go ahead and before I do this problem, I want to get to Amelia's question. Question 3 from the independent practice for section 10.2. Let me go ahead and pull up that file, section 10.2. And here is the independent practice, problem 3. Let's see. Oh, yes. Was I actually going to go over that one? Oh, yeah, I got it written down here. Okay. So, Amelia, for this problem, let me get the live chat back up in case people have questions. So for this one, should remind you of what we did with exponents, okay? We have one expression here, and we have another expression here, but this one has a 10 on the outside of it. So if we're going to go and try to simplify everything, well, I'm not going to simplify the first one just yet. But this one, we can use the power rule for it. So if you remember the power rule, that said we could distribute, and again, I'm using that word. If you can see me, I'm putting air quotes around that. We really said apply the 10 through. It's not really the distribution property, but you can think of it that way. So when I apply 10 to each of these exponents, what I'm saying to do is, and I'll write it all out here, multiply 10 to each of the exponents. That's what the power rule said. Or I think if you remember, it's the power of a product, I think was the specific rule. So we distribute or we apply the 10 to each of these. And then we have a to the negative half to the 10 power. That just means to multiply them together. So we have a to the negative 5 power. And then we have b to the 3/5 times 10. Well, let's see. 3/5 times 10, that's 30 over 5, which is just the 6 power. B to the 6th. Okay. Now, I like doing this first because it gets rid of, it allows us to work with these values. We couldn't before because we had the 10 on the outside. So we're going to go ahead and distribute it. Once we do that, now we have things that we could work with. So hopefully this part makes sense. If it doesn't, let me know. I'm happy to go back over that section. But now what we'd like to do is we have a bunch of terms here, right? 4 separate things all being multiplied together. Some of them are positive and some are negative. We said back when we were doing exponents, it's probably easier before we go and combine things to just move all the negative terms around. Remember, if you have negative exponents, what that means is move them to the other side of the fraction line. So it's kind of like a game of keep move. So let me write a big fraction here. A to the negative 1/3, keep or move. We're going to move that to a to the positive 1/3 power. B to the half, keep or move. We're going to keep that up top because it's a positive exponent. A to the negative 5th, we're going to move that down to be a to the positive 5. And b to the 6th, we're going to keep because it's a positive exponent. Now, we can go and combine these together. We would really just have b to the 6th times the square root of b over a to the 5th times the cube root of a. But wait a minute. Hopefully you're saying, okay, this part makes sense, but I know I cannot have a cube root in the denominator. So we have to do a couple extra steps here. We have to get rid of that cube root. So we have to rationalize the denominator by multiplying the top and the bottom by some value that gets rid of it. So since it's a cube root, I'm going to stick with cube roots here. I have 1a in this radicand. To get a cube root, I better multiply by an extra 2a's. So let me do that to the top and the bottom. And let's see what we end up with. I'll just move my work over here. In the numerator, don't worry about it. It's b to the 6, square root b, cube root a squared. I'm not too worried about combining all of that together. But on the bottom is where I really want to see things simplify. We have a to the 5th times the cube root. We had 1a before, now we added 2 to it, so that's a cubed. So when we have our fully simplified answer, we have b to the 6, the square root of b, the cube root of a squared, and then the bottom, we said that's just an a, so a times a to the 5th is a to the 6th power. I don't think I actually went and combined the radicals together. We could, but I don't know. Sometimes it's just a little tedious, and it's kind of fine left. Yeah, see, I just left it as is right here. Yep, see, I just kind of left it as is, or you could go and actually combine it. Doesn't really matter for me. I'm not too picky about this. I mostly just want to see that you are able to get rid of the radical in the denominator. So this is fine, or the combined answer I have is fine. Does anyone want me to go over how I actually combined these fractions together? I see Kylie, you want me to do problem 6 from the independent practice. You got that. I'll go over that one next. But Amelia, or anybody, I guess, do you have any questions about how we got to this part, or then how we went and actually simplified it down? And does anyone have any questions about how we might have gone and, in the answer key, how I went and combined these radicals together? If you do, let me know. I'm happy to go back over that and review that idea of multiplying things of unlike indices. Before, they weren't. That's like when we were doing the multiplication practice from section 10 point, I think it's 10.5, when we had to multiply unlike indices. It was a little kind of odd to do, but when we have it, when the idea of turning things into rational exponents, like section 10.2, hopefully it makes it a bit easier. Not seeing any questions that anyone... All right, looks good then, Amelia. Okay, so then we're going to move on. I don't see any other questions about how to go over this, so let's do Kylie's problem. Section 10.2, practice problem number 6. Let's see here. Oh, looks like I was going to do 7. So let me move to problem 6 really quick. All right. Oop, I just missed it. Oh, yeah, this was kind of a messy one. Let me get a clean sheet of paper here. All right, let's start with m to the negative 1/4 power all over n to the negative 1/2 power, and this whole thing is to the negative 4 power. Okay, couple ways of going about doing this. And again, I hope people remember or recognize that these look very similar to the work we've done before with exponents. Now, Kylie, there's a couple ways of going about simplifying this problem. I'm going to do both ways, and you decide which you like. Some students like one method, other students like another method. Now, the first thing is sometimes people like to, and I'll write this as part 1 or version 1, some people like to simplify inside first, then, that's a terrible then apply outside. What I mean by that is people sometimes like to simplify the inside of the parentheses first and then apply the outside. I call that the order of operations method, right? Simplify inside the parentheses first, then apply the exponent. Other people like to apply the exponent, then simplify. These people, I like to describe their method as the distribution method. Remember, distribution allows us to get around the order of operations by first applying the exponent through and then simplifying. So you pick which method you like. I'll do both of them. I'll do the first one in blue, method number 1. And this is where we simplify the inside first and then apply the exponent. So, can I go and simplify the inside? Well, yes, we have a way of simplifying it because notice these negative exponents. Okay, we never like working with negative exponents. What they mean for us is to move that term to the other side of the fraction line. So if I have this fraction expression here to the negative fourth power, what m to the negative 1/4 means is move that down here. So you have m to the positive 1/4. And n to the negative 1/2 means to move it to the top. Okay? Again, we just move the things that have negative exponents. Then, this is fully simplified. There are no terms for us to combine. That's as much as we can do. Once we're confident that it's fully simplified, we can then apply the negative 4 to each of these. So we could do n to the 1/2 power times negative 4, and then m to the 1/4 power times negative 4. That's just going to be, let's see, n to the 1/2 times negative 4. Half of negative 4 is negative 2, so n to the negative 2 power. M to the, let's see, 1/4 times negative 4 is just negative 1. Okay. Now, as we distributed or applied that negative 4 through to everything, we're able to get whole numbers. Hey, cool. It worked out nicely. It's almost as if I planned that. But now we'll notice, again, we're back to having negative exponents. This time we're going to have to simplify again to get m on top and n squared at the bottom, okay? That's the thing about when you simplify the inside first and then apply the exponent through. I actually like that method personally. I'm a method 1 person. I just do order of operations, simplify the inside first and then apply. The downside is you're going to have to simplify again at the end. Now, method number 2, just as valid, and a lot of times students prefer this. They like to apply the exponent to everything first. So let's do version 2 here, where let's take m to the negative 1/4 power, and I'm going to apply the negative 4 to that. And then we have n to the negative 1/2 power, and we're going to apply the negative 4 to that as well. So m to the negative 1/4 times negative 4. Okay, again, power rule just means we multiply these. We're going to have m to the negative, and negative makes positive, and 1/4 of 4 is just 1. And then n, we have negative 1/2 times negative 4. Okay, double negatives make a positive, and half of 4 is just 2. So there we go. We actually get the exact same answer using just a different technique. And both are totally valid, right? You could use the order of operations to kind of guide your work. Again, a couple more steps, but sometimes people like it just because it's a little more obvious. I think I like it just because it's a little more obvious to me. But other people are like, no, I'm always used to distribution, so why not use that to simplify things down? And in fact, we have fewer steps that we need to do, and we only have to simplify once. So whichever method you like, totally fine. But let me know if you have any questions on this or any confusion on either method or any of the steps. So Kylie, if you have any further questions about that, let me know. Or if anyone else has any questions about any of these methods, let me know as well. Hopefully we're seeing that this really fits into the work that we're doing, or we used to be doing with exponents, I think way back in Unit 1. It's just we've changed them up now to have fractions, okay? So again, the rules that we had before all stay the same. It's just now we have to work with fractions. Now, Gene, I see, can we go over the exit ticket problems? Yeah, we did the first one just a couple minutes ago, so let me jump back to that one. And again, I post these videos, so if you have any questions on them, we can go back over them. And you can always check back on the video. Here's what we did for exit ticket 1. Oh, good, Kylie, I'm glad. So, Gene, here's what we did for exit ticket 1. The big thing is that we said we have to add the exponents together because we're multiplying like bases. So we went and we added them together to get 17 over 12, okay? So we said x to the 17 over 12. I think in the directions I asked you to write that as a radical. We remembered from the previous lesson that the exponent is always the numerator and the denominator is the root. So we said this is going to be x to the... Oh, the second one from 10.4. So exit ticket 10.4. Sorry, there's like a 30-second delay on this. No worries. All right. Yes, we'll go over exit ticket 10.4. I think I might have done that one in a previous video. Let me check. But Gene, if we could hold off on that for just a minute, I want to do one more problem from section 10.2, and then we'll jump to section 10.4. Sound good? I'll wait. I'll just assume you said yes in 30 seconds. All right, cool. This is one I had a student that was asking me about the exit tickets from 10.2. So we did the first one. Here is a version of what the second one looks like. I'll wait to do the second one. I'll actually cover that in my 2 o'clock live stream later today. So remember, I'm doing a second live stream, same topics, but different problems. And if you have any further questions, tune in at that time and let me know, or just shoot me an email. That's from 2 to 3:20. Okay. So this should look similar to the one that we did, the second problem on the exit ticket, where we have a whole expression raised to a fraction exponent. Now, in this situation, we could think of it like this, okay? We're taking everything to the 1/3 power. We're cubing everything. But I don't like just writing it like this, because a lot of times students write it like this and they go, okay, cool, done. They don't actually go and simplify things down. So it might be helpful to think about this similar to what we did with our work before, where we took the root of each thing individually. Let's apply this through to each thing individually. So let's take 8 to the 1/3 power, x to the 4th to the 1/3 power, and y to the 2/3 to the 1/3 power. Okay, now 8 to the 1/3, that's just the cube root of 8. And then this is really the cube root of x to the 4th. And this becomes y to the 2, and 3 times 3 is 9. Oh, we have 2/9 here. Okay. Again, when we're doing the power rule, we have to multiply these things together. So 2/3 and 1/3 make 2/9. Okay. So this is actually going to be, let me rewrite this. This is actually going to be the 9th root of y squared. Okay. So this one's going to be a little different. It's going to have a different index for us. So let's keep going. Let's try to simplify these down. The cube root of 8, well, that's just a 2. And then we have the cube root of of x to the 4th. Well, that's the cube root of x cubed and the cube root of x. That's how I'm splitting up x to the 4th. And then we have the 9th root of y squared. Hopefully you're seeing that this isn't going to simplify down, right? The index says you need to make groups of 9, and you only have 2 y's. So, yeah, that's not going to break down at all. But the cube root of x cubed does. That just becomes an x, and we're left with the cube root of x and the 9th root of y squared. All right, let's go ahead and try to combine these indices together. So that's the question. How do we go about and do this? How do we simplify these indices to make one thing? Well, it's helpful, surprisingly. We could go back to what we did in section 10.5 and try to change around the indices and the exponents, but sometimes it's actually helpful if we just turn them back into rational exponents, because somehow working with fractions actually makes it a bit easier. So let's take 2 to the x, and let's change the cube root of x into a fraction, or into a fraction exponent. That's x to the 1/3 power. And then we have times y to the 2/9 power, just like we had originally. Okay. if we want to put these into the same radical, right? We want them to be both under the same radical sign. That means we want them to be under the same root. Okay? To be under the same root, they have to have the same index. Well, this one has a 3 and this one has a 9. Oh, gee. How can I go about and changing that 3 into a 9? Well, hopefully, you're saying, well, just multiply the top and the bottom by 3 over 3, right? Just change the fraction around. So we have 2x, and then we have x. Instead of 1/3 power, we have the 3/9 power, okay? Isn't 3/9 the same thing as 1/3? Hopefully you're like, oh, I see how we're getting that. We're just using our properties of fractions to get these to be the same denominator, right? That's why when we were doing this back in section 10.5, when we were multiplying radicals together, we were saying, oh, we really have to get the same index. So we were forcing it to be the same proportion. Now we're forcing it to stay as the same fraction, or the same, I guess the same type of fraction, or the same proportion. So let me write the final answer in blue here. We have 2x, and then we have, okay, we're taking the 9th root of each of these things. So we're going to have to take the 9th root of x cubed and y squared. So this is what we were looking for in the problem 2 of the exponents. We're looking to see, can students go and first apply an exponent through to each thing to simplify it down as much as they can. Then we were looking to see, can you combine the two fractions together? The two radicals together. Doing so, really, by changing them into these fraction exponents. That really became a lot easier, we tend to find, than when we were just using the 10.5 method that we learned back last week. If you have any questions on this, please let me know. I'm happy to go back over anything or to review anything. Again, I'll be doing the specific problem number 2 at 2 o'clock later today, for my second live stream between 2 and 3:20. And this video will be shared and posted so people can go back and take a look to see what we did and what we reviewed. But with that covered, I think we're going to get to Gene's problem. Gene, you were asking about the second problem from exit ticket 10.4. That, if I remember correctly, was the adding and subtracting of radical expressions. So let me go and pull that one up. Let me see if I can get it copied down. Oh gosh, this thing doesn't want to move. All right, let's see. 10.4. And the exit ticket for that one. And the second one. Yes, okay. So this was a big cube root problem that we have to do. So let me copy this down really quick. Let me get some spare paper. So this is section 10.4, problem 2 from the exit ticket. All right. Let me write this in black because I'm going to need some color coding later. The cube root of 256 x to the 6th power, y to the 1st power, minus 7x and the cube root of 108, x cubed, and y. Okay, one of the things that I'm going to do right away, Gene, is simplify each of these down separately. Just because I don't like stringing everything together in one big expression. So I'm going to simplify the first one in blue, and the second one I'll simplify in red. Okay? If you have any questions about how each thing is getting simplified, let me know. I'll pause my work and we can go back over it. Let's start with the cube root of 256 x to the 6th y. So we have, I was going to do that in blue. So we have the cube root of 256. the cube root of x to the sixths, and the cube root of y. Okay? Now, 256, let me break that down here. 256 could be 2 and 128. 128 is 2 and 64. 64 is 2 and 32. 32 is 2 and 16. 16 is 2 and 8. That's 2 and 4. 2 and 2. Okay? So I just did a prime factorization, got all the prime factors, and it looks like 256 is actually 2 to the, let's see, 1, 2, 3, 4, 5, 6, 7, 8th. So 256 is really 2 to the 8th power. So let's take the cube root of 2 to the 8th power, and then we have the cube root of x to the 6th. I'm just not simplifying anything just yet. I'm just doing it one step at a time. So let's go ahead and let's break down 2 to the 8th. The index says we want to make groups of 3. So let's see. I can make one group of 3, and then I can make another group of 3. That's 6. And then to get to 8, well, I have just 2 left over. And that's fine, right? It's not going to simplify down to a whole number, but that's okay. And then we have still the cube root of x to the 6 and the cube root of y. Okay. Hopefully you're seeing first how we broke the number down into its prime factorization, then how we've grouped things together. Since I had 8 2's, I grouped 2 groups of 3's and 2 left over. So hopefully that part's making sense. Let me know if you have questions on it. But let's go ahead and let's actually start simplifying these components down. The cube root of 2 cubed is just 2. The cube root of 2 cubed again is just 2. The cube root of 2 squared, well, that doesn't simplify. So we're left with the cube root of, I'll just call it 4. Now the cube root of x to the 6. Did you use or know? What do you mean twin method? Do you mean the prime factorization thing that I did? I'm not saying that I cheated, but I actually already had it written out. So off the top of my head, I had it already written out, but I would just grab a calculator and start doing those individually. So let me know what you mean by that, Gene. I don't know what the twin method is. But hopefully you're seeing that we were able to rewrite 256 using the prime factorization. So we got several of these 2's that we could group together in pairs of 3. That's the thing. With the index being 3, we want 3 things all grouped together. And then we have the cube root of x to the 6. Well, let's see. We have 6 x's and we're asked to make groups of 3. That's just x squared, right? And hopefully you're seeing now that you know about these rational exponents, the cube root of x to the 6th is really x to the 6 over 3, which is just x squared. So hopefully you're seeing that. That's why we're able to really just divide it by 2. But it's the same idea as saying, well, you have 6 x's and you want to make groups of 3. So that's that. Thanks, Gene. Yeah, send me a picture through my email. Let me see what question you have with that. Now, the cube root of y is our last one, and obviously that's not going to simplify down because we only have 1 y when we need 3. So our final answer for the first part should be 4 x squared, and then we have the cube root of 4y. That's really what we have for the first one. We simplified it down to get 4x squared cube root 4y. Okay? I'm going to erase this work, and then we're going to simplify down the cube root of 108x cubed y. Again, I saved these videos, and I'm going to post them once we're done, so you can go back and take a look. So let me clear some space here. And I'm going to switch up colors to work with the red problem. Let's see. Now we have the cube root of 108 x cubed y. So let's take 108 and let's break that down. We have 2 and 54. 54 can be broken down into 2 and 27. And 27 can be broken down into 3 and 9, which can be 3 and 3. Okay, so let's go back and let's rewrite this as the cube root of 108 is 2 squared and 3 cubed. Notice we have 3 3s and we have 2 2s. Okay, so that's why I'm writing 108 as, instead of the cube root of 108, I have the cube root of 2 squared and the cube root of 3 cubed. We also have to take the cube root of x cubed and the cube root of y. All right, let's see what simplifies down. The cube root of 2 squared, that's not going to simplify. I need 3 things per group, but I only have 2 2s. So that first one doesn't simplify. But the cube root of 3 cubed simplifies to 3. The cube root of x cubed simplifies to x. So what we're left with is the cube root of 4 and y, because these things aren't going to simplify down. So let me write that up here. We have 3x cube root of 4y. Hopefully, again, this part's making sense, how we're going and simplifying things. One thing I always say to students when they're going to try to add or subtract radicals, a lot of times people just take a look and they say, hey, these radicands aren't the same thing. We can't go and simplify these, or we can't combine these together. Always make sure you have to check, will they always simplify down to have like radicands? Well, in this class, most of the time, yeah. But in reality, right, if you're trying to add or subtract radicands or radicals together and you simplify them down, will their radicands be the same? No, not always. So you have to check to just make sure. So let me go ahead and let me clear some space, and we can substitute in what these expressions are, these simplified expressions, and let's see how they combine. All right, I'm going to go back to black here. So the first thing, actually, I did that in blue. The first thing was 4x squared, and then the cube root of 4y. That was the first radical. And then we said, let's subtract 7x times this whole radical. Well, we simplified that down to be 3x and the cube root of 4y. So when we go and we combine these together, or we simplify some more, we get 4x squared and the cube root of 4y minus 7 and 3 makes 21, x and x makes x squared, and we have the cube root of 4y. Okay, we need to see, can we actually now simplify these by combining them together? So, 1, they have the same radicands and the same indices, right? They're both cube roots. So we're good there. They're like radicals, right? They have the same radicand and the same indices. But we also have to check, can you actually add the things on the outside? Because that's how we go about adding them together. We add the kind of the pseudo coefficients on the outside. So can you add 4x squared and negative 21x squared? Well, luckily in this case we can. They are like terms. I think a couple of the practice problems I had it where they weren't like terms, where you had to check to make sure like, oh, actually they're like radicals, but the things that we're adding together don't actually combine. So you had to just leave your answer as is. But here we can. 4x squared and negative 21x squared. What's that? Negative 17x squared. Negative 17x squared. And the cube root of 4y. That should be our final answer. Let me know if that clarified everything. The big component when working with these, because these problems aren't that bad, right? I mean, you know, of all the work that we've done before, like, they're fairly simple, and we've had a lot of practice in these. It's just they're tedious, right? They're kind of more elaborate. So just make sure that you're able to, I like grabbing scrap paper. I like color coding things, working one color for one color for the other, and then showing how they substitute things in, and doing it one step at a time. So let me know if you have any questions on this. And then, Gene, you were going to email me that one question you have too, and we can go back over that some more. But hopefully this part makes sense. Amelia's asking, do you have any idea when the Unit 5 test is going to open? Yes, actually, so if you check on the assignment sheet for this Unit 5 Part 1, on the Weebly website, you'll see it's actually going to open tomorrow. So the Unit 5 test is going to open in Edulastic tomorrow, and it's going to run a week, just like we normally do. Okay? And again, when it comes to the test, just like for the Unit 4 test, I'm still in the process of grading those. I go through each question individually to see how students answered them. So sometimes people answered things correctly, but in a different version. Other times people put the correct answer in, and for some reason it was marked wrong. Maybe they put a space in it or something. So I'll check over that. So don't worry about that. So I'm going through, and I go through, and I also give partial credit. So it's not like all or nothing. Edulastic calculates things all or nothing, but I actually go through and try to assign as much partial credit as I can by just looking at your answers. Oh, good, Gene. I'm glad that this makes sense now. Yeah, that's one of the little tricks is sometimes we always tend to forget about, oh, wait, there was something on the outside there. Are there any other questions, any other things that you want me to go over, take some time to review? I'm happy to do that. You know, I say these live streams, I pick a couple problems just in case people don't have anything to go over. But, you know, this live stream is your time. So let me know if you have any other questions or things you want me to review. Again, since I mentioned the Weebly website, make sure to be checking out linfordmath.weebly.com. Today's activity is just the practice test for Unit 5. But tomorrow, starting at 9 o'clock, actually, you'll see the exam open up. I'll have a link posted on the Weebly website. But it's also going to be through Edulastic. So you can either log in through Edulastic, or the Weebly you can click on the link and it will take you to Edulastic. And the Unit 5 assessment will be in there for a week, pretty much. Whatever it says on the assignment sheet under Unit 5 on linfordmath.weebly.com. Feel free to let me know any questions also that you have. Any further questions about the video or comments, you can comment them below. But a quicker way is to just shoot me an email at klinford@wccnet.edu. That's KLINFORD@wccnet.edu. I'm going to have a second live stream starting at 2 o'clock, and we'll run through at least 3:20. Let me know if you have any questions you'd like me to go over at that time, or any questions you'd like me to go over right now. I got another 15-20 minutes if anyone has anything that they'd like me to review. Otherwise, I might just end this early. I also have office hours available later today, so feel free to sign up. You can do that at linfordmath.weebly.com under the Contact tab. So for office hours, visit the Contact tab to sign up there. It's all done through Google Calendar. If there are no other questions, doesn't seem like, hopefully this was a good enough review of Section 10.2. We're going to go over a couple more problems starting at 2 o'clock, especially we're going to review the second problem from the exit ticket. So if there are no more questions, which it doesn't seem, I will end the live stream a little early. Feel free to shoot me any emails and let me know starting or for the next live stream, which starts at 2 o'clock. If you can't make that, don't worry. I'm going to have another one on Wednesday starting at 9 a.m. So if you have other questions, feel free to let me know. Wednesday starting at 9 a.m. I'll be able to go over those as well. Hopefully this was helpful. Again, let me know any questions you have or comments, and I will see you later.